Okay, in this video, let's take a look at the minimum height that something needs to be dropped from in order to make it through like a loop-the-loop or something. So kind of if we look back at what we had in a previous video, you know, some platform here, and then maybe we have, it goes down, and then we have like a loop-the-loop here, and maybe we had there was like a ball up here, started out. Maybe it started at rest, so I could call here, this is like V1 is equal to 0. The ball rolls down and it goes through this loop and etc. I can set my datum here. Let's say that we just have a reference height. This height is equal to 0 here. And let's say I just want to know what this height needs to be here. What is this h? So that if this starts at rest, this red ball starts at rest up here, what minimum height do I need h so that it can actually make it through this loop? This is the most critical point right here, right? If it makes it through this point, it'll make it through everywhere else. And so I just want to make sure it makes it through there. So I can label my 2 points, and we'll assume that this is all frictionless in here. If it's not frictionless, we'd use the work energy theorem. But let's say that this is point 1 over here, where it starts out at rest, and then this is point 2 right here, where it's at the top of the loop. So I know some things about V1, and I'm looking for H1. But I also know some things about V2 from what we derived in the class with the swing in the pail of water. Then we have we know that V1 is equal to 0, and we know that the minimum speed at 2, so I'll call this V2, well actually just V2 must be greater than or equal to the square root of RG, right? So the minimum speed, because I want to know what is the minimum height here. The question is, what's the minimum height h to make it through the loop here? So I'll calculate for the minimum speed. And so then V2 minimum is just going to be equal to the square root of RG. Okay? Where this R is the radius of this loop, right? So this would be R here. Okay? All right, so we know V1, we know V2. We also know something actually about the height at point 2, really. Right? If the radius of this loop is r, then this height at 2, call this h2, this is going to be equal to the diameter, which is twice the radius, right? So that's 2r. And so using conservation of energy, let's just say here we have the mechanical energy at point 1 must be equal to the mechanical energy at point 2. And so therefore we have the potential energy at 1 plus the kinetic energy at 1 is equal to the potential energy at 2 plus the kinetic energy at 2. And again, we don't have any springs or anything here. Okay. But we know that we started out at rest, so the kinetic energy at 1 is equal to 0, right? And so then writing out, just kind of expanding this for potential and kinetic and all this, we have mgh1. Did I call this h1? We'll call it h1 here. mgh1 is equal to mgh2 plus 1/2 m v2 squared. These masses actually all cancel out already, so we can go ahead and do that and simplify it down. And so we have gh1 is equal to gh2 plus 1/2. V2 minimum was the square root of RG, right? And so this is the square root of RG squared. Now we also note here that H2, remember this was equal to 2R, right? So I'll replace that. I'm also going to expand this here. And so we have GH1 is equal to G times 2R plus 1/2 of RG, right? And so actually each of these have a G in them as well now. So there's a G here and a G here and a G here. So all these G's cancel out as well. And so we have H1 is equal to 2R plus another 1/2 R. Or we could say H1 is equal to 5/2 R. So I need to, in order to have this make it through the loop, it's just, it's 2.5 times the radius. So I need to have something start, and this assumes, no friction, right? But basically, assuming there's no friction, then this height here has to be 2.5 times this radius. I get 2 of the radius, 2 of the radii, just to get the same height, right? And the other half of it is what I need to convert from potential energy here to kinetic here. I could have, if I wanted to, I could have solved this, and you should do this. Set your datum to be equal to 0 here. If you set this height, maybe set the height 2 equal to 0, and then solve for this new height here, called this height 1, then that'll just be equal to half the radius, 1/2 R. So it's relative to where you call your datum equal to 0 though. But I would need to, essentially what this would say here is that, actually let me write that out. So this height would be equal to 1/2 R. So it needs this much potential energy. The potential energy here needs to be converted to kinetic energy just to make sure it's going the minimum speed needed to make it through the loop that we derived previously. So, or if I take it from the bottom, measure from the bottom, then the total height just needs to be equal to 2.5 times the radius. So.